Welcome to module 7, lecture 4. We shall be continuing with the shrinkage of concrete mostly. Of course, at the end we will talk about a little bit about the thermal expansion of concrete. So, we talked about some understanding of shrinkage earlier. We will look at it at more details. Then we will look at shrinkage measurement, its relevance, and as I said lastly we will look at thermal expansion for a little while. Now, like creep, shrinkage is somewhat less understood, it is not fully understood. Shrinkage of issues in concrete is relatively less understood. Of course, if we want to understand it more, then we must look into physico-chemical fundamentals, and that is what we are trying to do right now. Now, to start that, we must understand what happens in liquid gas interface. For example, in liquid gas interface, when pressure is applied onto the liquid, the vapor pressure increases. You apply pressure to the liquid, this is your liquid, let us say, this is your liquid say, and you apply pressure here through a piston, you apply pressure here through a piston, then vapor pressure increases, molecules get squeezed out of the liquid phase and escape as gas. So, if you apply pressure to the liquid, liquid phase will get out, squeeze out and escape as gas. Now, if the equilibrium then is established, then chemical potential of the liquid and vapor must be equal. At equilibrium, chemicals, because there is no movement further, no movement is taking place. All right. So, for movement you need potential of one to be higher than other. So, you applied pressure to the liquid, actually increase the potential, therefore, the molecules will move out as vapor. So, therefore, if I write chemical potential mu L of the liquid must be equals to mu G at equilibrium, and if I have to preserve this equilibrium, any change in liquid potential through pressure change dP must correspond to a change in gas potential, right. So, if when I have applied pressure to the liquid, let us say dP is the pressure I have applied. So, liquid potential changed and correspondingly the gas potential must have also changed, otherwise equilibrium would not have been there, otherwise there would have been no equilibrium. So, therefore, d mu L, differential mu L must be equals to differential mu G, where mu L and mu G are the chemical potentials of liquid and gas. Now, one can write d mu L as V m L molar volume of the liquid into dP, because molar volume is not changing. So, P dV is the work done, P dV plus V dP. Since dV there is no volume change, so one can write as V dP. So, that is the work done, or that is the potential change of the liquid, and that must be equals to the gas potential change. So, gas potential change is similarly one can write V m G, that is vapor molar weight, into dP. dP is change in partial pressure. So, here when we are talking of the gas, it is a partial pressure, partial vapor pressure. So, it is a vapor. So, we are talking of partial vapor pressure, right. I am assuming that you understand what is partial vapor pressure. It is the vapor pressure exerted or the gas, pressure exerted by a gas when it occupies the full volume as the mixture. So, partial vapor pressure would change. Now, vapor can be thought of an ideal gas. Therefore, the V m can be written as R T by P for 1 mole actually. So, R T by P d P. So, d mu g can be written as R T by P, R T by P d P, and that must be equals to V m L P. Capital P stands for the pressure that you applied to the liquid. This is the partial vapor pressure of the vapor. So, therefore, if you integrate this both sides, so you will get ln P by P 0 must be equals to, if you integrate both sides, you will get, if you integrate this P dP by P, if you integrate, you will get ln P, putting the limits P 0 to P. So, vapor pressure changed from P 0 to P, and that must be equals to V m L by application of pressure dP. So, therefore, ln P 0 is equals to P by P 0 equals to V m L by R T dP. Now, this vapor pressure change can occur because of applied pressure or because of things like, because of phenomena like surface tension. Okay, so, algebraically we can write it like this: P by P 0 will be equals to e to the power V m L by R T dP. Right. Now, liquid. So, we are looking at the situations, this vapor pressure, this dP can change because of surface tension. So, just look at the fundamentals of surface tension. Liquid tends to adopt shapes to minimize their surface area, to have maximum number of molecules interacting with the neighboring ones. Liquid always try to adopt shapes that minimize their surface area. That is what we have seen. It takes the shape of the container and so on and so forth. It tries to minimize their surface area and to have maximum number of molecules interacting with the neighboring ones. That is the property of the liquid, and this is what leads to surface tension. So, the work done, work dW that is required, to change the surface area by, let us say, dA, small surface area dA is equals to gamma dA. So, dW is equals to gamma dA. This gamma is the surface tension. So, the surface tension is basically the work per unit area or energy per unit area, energy per unit area. This is the work required to change the surface area, because it has a tendency to attain a minimum surface area. So, if you want to increase it, you have to do work, and that work is proportional to the constant of proportionality is gamma. So, energy required per unit area, that is actually surface tension, that is actually the surface tension. So, that is the surface tension. So, minimization of surface area of liquid may result in formation of curved surfaces. Actually, so because of surface tension, the surface tension property of liquid, it results in formation of curved surface, because it tries to minimize the surface area. Therefore, when it is trying to minimize the surface area, it actually may result in formation of curved liquid surface, right. So, meniscus and so on, and usually the pressure on the concave side of the curve is always higher than that of the convex side, because concave side, this side the pressure will be higher than on this side, always it will be higher, because we will see that actually it will be higher, because the molecules will try to pull each other in a given way, and the pressure on this side is usually higher. So, let us say consider a curved surface with surface tension forces acting along normal to the perimeter. That is what it is, surface tension, because it tries to pull the surface, kind of a pull, it pulls the surface, tries to pull the surface, say something like this. So, this is a curved surface, and the surface tension force act onto the perimeter, because it is trying to minimize the surface area, and it acts onto the perimeter, either to stretch it as much as possible, right, stretch it as much as possible, so that the thickness is minimum, right. So, stretch it as much as possible, the thickness is minimum, so that surface area is actually minimized. So, if I exaggerate this and draw it in this manner, so basically this is the forces acting along this direction on an elemental surface, this will be the forces acting along this direction, this will be the force of F A D, F C D, F B C and F A B. So, these are the forces that would be acting. Now, if you look at these forces, the resultant force will be acting inward, this is the radius along this curvature, and the resultant force will be acting inward, because this is curved surface. So, the forces are like this and forces are like this. So, resultant forces will be acting inward, and one can write possibly in this manner, one can write after looking at the equilibrium, one may write an equation. So, resultant force will act towards the center, and pressure for the surface area results in what is called Young-Laplace equation. So, one can actually find out the resultant force acting inside, and this will be a function of R 1 and R 2, it will be a function of R 1 and R 2, and gamma is the surface energy per unit area, which means actually a force per unit length. So, unit of surface tension is Pascal per unit length, force unit per unit length, and multiplied by the length, multiplying by length in the perimeter, and finding out the resultant force, one can actually show for the unit area, one can show P inside is equals to P outside plus this. So, P in is always higher inside, that is within the concave side is always higher than P outside, and this is gamma surface tension, R 1 and R 2 is the radius of curvature in two directions that we considered. And if it is a spherical surface, then R 1 is equals to R 2, and I can write it as R, and Young's Laplace equation turns out to be P in equals to P out twice gamma by R. So, you see the because of the surface tension in the inside, there will be excess pressure of 2 gamma by R, and this excess pressure will result in change in the vapor pressure, because we said if you change in if you change the if you apply a kind of pressure, then there is a change in the vapor pressure as well, and this gives rise to Kelvin's equation. So, since the curving surface gives rise to pressure differential of twice gamma plus R, it results in Kelvin's equation, which is talking of, which actually is a model for equilibrium pressure at the interface of liquid and its vapor, all right. So, liquid and vapor, right. So, you see this is what is Kelvin's equation. We replaced the pressure dP by twice gamma by small r. I am writing r is the radius, because capital R is the universal gas constant, capital R is the gas constant, gas constant. So, it is a gas constant, therefore, small r is the radius of the capillary. So, it is a vapor pressure because of the surface tension change in the radius of curvatures, because of the change in curvature. P 0 was original before the formation of curvature, and now because of the formation of curvature, this will be the pressure, final pressure P 0 e to the power twice gamma by R V m L divided by R T. So, that is Kelvin's equation, can be written in some different form also, but that is Kelvin's equation. So, R is the radius of spherical surface, and at r equals to infinity, when r is equals to infinity, P equals to P 0. That means, for a flat surface, P is equals to P 0, and in under such situation no evaporation will take place. I mean, just let us say this is P, r is equals to infinity, at this stage, right, to start with, and this no evaporation is taking place. Now, as P changes, small p changes, r would decrease, or rather r changes, P would decrease up to the limit of the pore radius, because beyond the pore radius this r cannot be smaller than this. So, therefore, r changes up to the pore radius, and correspondingly P changes as well. So, correspondingly P changes as well, because it cannot be of this kind. Maximum, maximum curvature would limit to r equals to the radius of the capillary tube itself. So, if you are looking in a capillary tube, so this will be, the radius would be simply would be equals to r. So, pores gradually becomes empty according to their size from larger to smaller pores. Now, once this reaches r, further change in the vapor pressure would result in pore becoming empty. So, in the drying case of drying, vapor pressure changes. As the vapor pressure changes, the pore curvature will change, and a time will come when curvature radius of the capillary of this curvature of the surface and the radius of the tube is same. Beyond that, if still pressure changes, then what will happen? The pore will become completely empty. So, this is the phenomena of drying. So, drying actually, so pores gradually becomes empty according to their sizes. So, larger pores first get emptied and then comes to the smaller pores. So, typically this is the large neck, first this will get emptied and this is the inside at equilibrium. Of course, this will depend upon the vapor pressure existing and this size. So, capillary size, and that is how actually drying takes place. That is how drying takes place. Now, how it is relevant to our shrinkage? So, this is what it is. When such drying is actually taking place, this is the capillary, this is my capillary, this is my capillary, the equilibrium is existing at this point. Now, a tension would exist here, a tension would exist here. Water has a tendency to, because water has a tendency to, water has a tendency to spread, water has a tendency to spread, water has a tendency to spread. It will try to spread along this direction. So, if it tries to spread, the radius would like to increase. It is perimeter will like to increase. In other words, there is a tension acting in the water. So, the tension acting in the water is something like this, and this tension is maximum just at the bottom of the meniscus and gradually reduces down up to the surface of the water outside. So, if you have a capillary, water rises along this direction, water rises, and the tension in the liquid is of this kind, because liquid would like to spread, liquid would like to spread. Here there is no tension because it is already spreaded. Here liquid would like to spread. So, from here to the within the capillary, in this one there is a tension. Now, this in other words will actually exert a kind of compression onto this glass tube. So, it induces compression in the solid skeleton. Now, if it is within concrete or paste, cement paste, then it will exert onto the paste interface, paste capillary interface. So, the compression will be the paste matrix or paste skeleton will be actually under a kind of compression. Paste skeleton will be under a kind of compression, right. So, this will be under compression, this will be under compression. So, therefore, a molecule, if this compression, now let us look at this. If you look at the surface tension properties for the gel, same thing, similar kind like as liquid. So, a molecule will well below the surface is equally attracted by all surrounding molecule. For example, a molecule below the surface, it is attracted by molecules in the surrounding, attracted by molecules in the surrounding, but the one up there, one up there actually, one somewhere there will be attracted only downward, it will be attracted only downward, right, upward there is no force. So, that is, so therefore, if I bring in a liquid here, if I bring in some liquid here, liquid molecule here, which gets absorbed at the surface, then the force, downward force will get reduced. This downward force will get reduced, downward force will get reduced. So, downward force will get reduced, all right, downward force gets reduced, downward force gets reduced, all right. So, molecule at the surface is acted upon by a resultant inward force and surface tension results, right. And when I, for colloidal particles such as CHS gel, this is significant, for CHS system also this is significant, and compressive force induced could be as high as 250 MPa. So, if it is dry, there is a compressive force acting downward into the skeleton, and this could be as high as 250 MPa. Now, I bring in adsorbed water, reduces this inward compression and surface tension and swelling results. So, what will happen? It reduces down the inward compression. In other words, surface tension of the CHS system has reduced. So, swelling will result. There are no molecule. If there are no molecule at adsorbed water, then the molecule of the CHS or particle CHS system will pull the surface ones inside, and it would induce a kind of compressive force. Now, if there is an adsorbed water, this compressive force will get reduced. In other words, surface tension would reduce and swelling will result. So, adsorption of molecule results in swelling, adsorption of molecule results in swelling, right. Adsorption of molecule results in swelling, and swelling strain is proportional to the surface tension itself, right, and it is like this. So, the strain that results in, let us say, because of water being adsorbed, would be proportional to surface tension force, and constant of proportionality is k, which can be related to modulus of elasticity of the gel, which can be related to modulus of elasticity of the gel. So, you see the change in surface tension because of adsorbed water results in swelling, strains, and this is energy per unit area can be related to strain. Therefore, this must be related to the stiffness or modulus of elasticity of the system. So, this one is again related to vapor pressure. If we remember, this one is related to vapor pressure. So, if there is a vapor pressure change, this surface tension would change, vice versa. If there is a change, curved surface results in change in vapor pressure, and if there is a delta y change because of water being absorbed, it will also change in the vapor pressure. So, when some water gets absorbed, there is a change in vapor pressure, and there is a change in vapor pressure, and this change in the surface tension results in swelling. Now, if I withdraw the water, reverse will actually occur. So, delta y one can write it like this. This is for the moles, n moles adsorbed. If n moles are adsorbed, one can find out how much is the delta y from the change in vapor pressure or rate of change of vapor pressure, and so on and so forth. So, therefore, swelling takes place when moisture is adsorbed. And shrinkage takes place when drying occurs. So, when drying occurs, it will come to R will become smaller. As the moisture is withdrawn, R will become smaller, and my vapor pressure change would be, vapor pressure change would actually occur, and R would become smaller, and at this smaller R, the compressive forces onto the skeleton that would generate would actually compress the system, right. It will compress the system, surface tension will change, and it would actually compress the system more. So, there is a compression because of the capillary itself. There is also compression because of the adsorbed water being withdrawn. So, this results in drying shrinkage. So, adsorbed water reduces surface tension, surface energy, hence critical stress initiating fracture from the pores will also be lower. So, since the surface energy becomes low, if you recollect when we are talking of strength, strength is a function, critical stress is a function of E t under root E t divided by pi into half of the crack width or pi r. Now, surface energy is reducing when actually moist, it is becoming moist, and therefore, critical stress reduces, therefore, moist specimen exhibits lower compressive strength due to this dilation effect. So, this is going back to our situation. Two things: first of all, if water comes in and it is adsorbed at the surface tension reduces, and the compressive force which was pushing the gels matrix together, now there will be a dilation. So, it expands. but at the same time surface energy reduced, therefore, moist specimen shows lower strength. Now, when I withdrawn the water, what will happen? This surface tension in the gel will actually increase, and therefore, the compression in the system, it will compress the gel particles inside, and therefore, its dimension change would occur. So, during drying. Besides that, in the capillaries there is a tension in the liquid itself, which tries to which in turn tries to kind of compress the skeleton. So, capillary, when there is capillary water, depending upon the capillary size, it would actually there will be a compression. So, this compression, this compression results in dP changes in the liquid, which in turn would actually cause a kind of compression to the skeleton, both to this could provide explanation to drying shrinkage. So, first of all, when drying occurs, adsorbed water is moved out, there is a the pull by the gel particles at the surface by the inside particles becomes more, there is a kind of compression. So, there is a shrinkage, and also there is a tension at the in the liquid itself, which wants to spread, and it pushes the particle out. So, when there is a drying, this phenomena actually pushes this phenomena, it comes to the finer and finer pore, and this pressure is actually twice gamma by r. So, r becomes smaller, this pressure would increase, and it would actually exert more compressive force onto the skeleton. Therefore, these are the phenomena through which one can explain the drying shrinkage of cement paste or concrete. And also by using same phenomena, we are able to explain why moist specimen shows lower compressive strength. If you recollect, we said that when specimen is moist, it exhibits lower compressive strength. That is because the stress it can withstand is less. That is because the kind of a dilation would occur, surface tension reduces, gel particle expands, system expands, and it can actually the surface energy is reduced, therefore, it requires lesser force or lesser stress to actually cause fracture. So, both the two phenomena, this same phenomena understanding gives us the why moist specimen shows lower strength, but it also gives us some understanding of shrinkage, drying shrinkage process. So, what is it? First is a chemical shrinkage is a small quantity in the beginning, and autogenous shrinkage is larger quantity, drying shrinkage would follow. So, this is various shrinkage we looked, and then measurement must then cater for all these types of shrinkages, which we discussed earlier in our previous lecture. Well, Indian standard recommends a length comparator, something of this kind for shrinkage measurement. So, you have basically this, there is a dial gauge, you put your specimen here, and there is a standard, you put your specimen here, and any length change you can measure. Basically, there is a standard reference which first is used to find out what is the dimension, and you have actually a Dirac point here on the specimen, Dirac point here on the specimen. So, there is a tip which comes and matches, and this dial gauge can tell you what is the dimensional changes. So, this can be used for measuring length change, and if it is sealed specimen, then that would give you a kind of chemical and autogenous shrinkage maybe together. While if you look at Leach-Atelier's method, which is also measuring dimensional change in cement paste, and it is contained in sealed rubber bag, contained and sealed in a rubber bag, and volume changes are determined by the weight change in water. So, whole sealed bag you can put it in water and any change in volume together with the rubber bag, because rubber will expand or contract according to it is because it can expand or contract. So, according to the expansion or contraction of the specimen. So, as the specimen contracts, rubber bag will also contract, and its volume change you can find out. That is Leach-Atelier's principle. However, chemical shrinkage can be measured by ASTM C1608 method, and restraint shrinkage can be measured as per ASTM C1581 this method, right. So, 15818 method. Now, chemical shrinkage method, how do you measure? Well, you measure it like this, you measure it like this, you have actually cement paste here, and then you fill it in with water, and then there is a capillary which is graduated, and you put in excess water just after mixing, after mixing, all this is happening after mixing. So, you fill this with water, and this is all water, and there is a paraffin oil added at the top to minimize any evaporation. So, there will be no evaporation loss, and as the shrinkage of this one occurs, this capillary will come down, and from the graduated capillary you can actually measure the amount of chemical shrinkage. So, chemical shrinkage is because of the volume change of this one, right. So, volume change of this one. So, as the volume of this one shrinks, this can volume change, full water is there is no evaporation loss, nothing, no drying, nothing is occurring. So, volume changes, as we discussed, that stoichiometrically you can find out how much volume change of the product would occur. So, you can measure this chemical changes. This is done in the early stage. Now, the other one is through shrinkage measurement is through ring test. This is called ring test, where you have, this is your outer ring, and this is the specimen hatched one, and this is the inner ring, right. This is inner ring actually, and then you can use strain gauges to measure. So, this is a ring test, it looks like this: outer ring, concrete, inner ring, right, and various kind of arrangement. Of course, there is a base here, and this is your concrete, this is the inner ring, and there is the outer ring, some dimension d, etc., etc. These are given in the code itself. This is called ring test, and in this one typically it looks like this. You see, you can see the concrete here, and outer ring, the inner ring somewhere there, and inner ring you put in strain gauges, inner ring you can put in strain gauges. This diagram is showing actually demolded specimen, polythene, then they are covered with polythene sheets, they are covered with polythene sheet, with the inner ring still intact, they are covered with polythene sheet, and this is also showing actually the ring situation, and this is the demolded ring. So, it is covered with polythene. Now, you have strain gauges, and you can go on recording the strain, because as the shrinkage occurs, this dimension will try to reduce, because this inner periphery will try to reduce, and therefore, in turn it will exert a kind of pressure inside this, the perimeter of this one will try to reduce. There is an inward, is just opposite of a kind of hoop action inward, trying to reduce the, since it is shrinking, perimeter length is trying to reduce. So, radius will try to reduce, and there will be strains, and these strains you can go on measuring with time, and that will give you all kind of shrinkages. For example, autogeneous shrinkage, and in the long run, if it is a shrinkage, drying shrinkage up to cracking. If you have autogeneous shrinkage, means you have actually covered it with polythene, no moisture loss should be there, but if you allow it to dry in a given environment, then you can find out what is the time required for cracking. So, this is an STM test, and that is how we measure. So, restrained shrinkage, of course, now typically before that I can just draw a figure, I can draw a figure, essentially a figure would be something like this before this effect of shrinkage. So, you have actually shrinkage strain, with time you plot for ring test, and this is with time it will vary for different conditions, and you can find out. So, with time hours, in terms of hours or days, as much as you want to measure, and these strains can be related to shrinkage. So, this strain is a kind of can be related to shrinkage. So, in your ring test, the inner ring shows you, this is your concrete, the strain gauges have been put in there, So, this strain gauges, for this strain gauges you can measure the strain, and that would tell you how much is the shrinkage actually occurring. From this you can calculate out the strain that would be occurring. So, that is called the ring test. Now, what is the effect of shrinkage? So, that is how we do the test. So, chemical shrinkage is measured by change in volume through a graduated capillary, and autogeneous shrinkage as well as drying shrinkage up to cracking can be measured by ring test. That is what I just mentioned. You can go on recording this. So, this is what is a ring test from which you can measure. Now, what is the effect of shrinkage? effect of shrinkage is restrained shrinkage can cause cracks in thin section. For example, if you have a wall, it is a wall like this, thin wall, right, thin wall, and is restrained. Construction joints are not given, have not been given, let us say. You might find cracks like this, at regular spacing, especially if the curing is improper. This is not very uncommon in thin section, something like 200 thick to, let us say, 200 to 300 at the bottom, because if you remember, we said it depends upon volume to surface area ratio. So, if the curing is not adequate and drying is occurring in a thin section and there is no construction joint, it is a long wall, let us say a basement wall 30-40 meters without proper construction joint, this can result in cracks coming in all through. Thin section this comes. Precast elements, thin, very thin precast element. If it is shrinkage is restrained, cracks can come, and it could be through and through. It could be simply through and through up to certain depth with a larger crack here and finer at the bottom, or may not go up to full depth, something of this kind. So, this is a phenomena seen in northern India, especially when you cast the concrete around May, June, when relative humidity is very low, 10 to about 40%, and the curing, if it is not done properly, this can result in cracking, and these cracks you see normally within 2 to 3 months of the construction, drying shrinkage cracks, that is fairly common. High strength concrete are susceptible to autogeneous shrinkage. High strength concretes are susceptible to autogeneous shrinkage, because you have a lot of cement paste in the system, and therefore, they may be susceptible to shrinkage. So, one has to see that, one has to so therefore, this is studied for low water cement ratio system, autogeneous shrinkage studies are important. Tall building, very tall building, this is your outer column, let us say, outer columns, and where you have somewhere you have got inner columns. Now, drying here, drying is different than drying here, drying in this one, drying, they will be different. So, this could be shrinking more if it is drying more, or depending upon the situation. So, if one shrinks, if there is a differential shrinkage or strain due to the shrinkage in a very tall building like creep, differential creep, because in case of creep, loads were coming different. Internal columns were highly loaded, where external columns were less loaded. So, in tall buildings, loading, because of loading, the creep effect comes in, but external columns may be drying differently than the internal columns, depending upon of course, the climatic situation. And if there is a differential strain coming in very tall building, 30 to 40 story building, then you might find there are secondary because of this there are secondary moments that is coming in, because of differential shrinkage, this may result in additional moment, like we discussed related to creep. Loss of pre-stress is of course, the other effect. Loss of pre-stress is of course, other effect, because shrinkage means shrinkage with the natural dimension of the concrete would become smaller. So, there will be some amount of if it is restrained, then there will be, this would cause loss of some pre-stress, because it would have tried to come to this dimension because of shrinkage, but you have restrained it. In other words, you are actually applying a kind of tension. So, the pre-stress loss can be there because of the shrinkage of the concrete itself, because of the shrinkage of the concrete itself. So, this is another effect. But most important, of course, is the cracking, shrinkage cracking. If it is restrained, then tensile stress may be increasing like this. This might be the induced tensile stress because of the restraint, and this will change with time, because shrinkage will increase with time, therefore, stress will increase with time. Shrinkage will increase with time, therefore, stress will increase with time, right. And this is the tensile strength. So, in the beginning, shrinkage is less than the tensile strength, shrinkage could be less than the tensile strength, but if the shrinkage crosses the tensile strength, cracking would come. Fortunately, there is some amount of relaxation because of creep, because you have a tensile stress which is sustained with time. So, there will be some relaxation due to the creep effect, because there is a sustained tensile, because it is restrained structure. Restrained structure shows shrinkage cracking. I was talking about the thin structures earlier, very thin sections, in the similar sections actually. This is long, there is no construction joint in the basement wall, thin basement wall. Evaporation rate is higher, V by S, volume to surface area ratio. V is small, S is large. So, V by S is small, thickness is less. So, therefore, V by S is less, and there the evaporation rate is high. Curing has not been done properly. One might have used even an accelerator to accelerate the strength gain or similar kind of thing. So, basically where curing is not proper, this scenario is seen much, particularly in the hot dry desert sort of climate where relative humidity is very little, or in a composite monsoon climate during the hot dry desert season. So, shrinkage will increase with time, tensile strength also increases with time, but since it is sustained and restrained, therefore, there will be some relaxation. Sustained stresses would be generated because of the restrained shrinkage, but this also get relaxed due to the creep. Creep relaxes it. We said that if you sustain loading, if it is restrained, then there is a relaxation. So, this is the relaxation, this is the relaxation due to creep, this is the relaxation due to creep, right, this is the relaxation due to creep. Now, tensile strength increases in this manner. The moment tensile strength is less than this, because shrinkage increases with time. Relaxation is also increasing with time, but a time comes when actually this net tensile stress overtakes the tensile strength, the cracks actually develops at that time. So, this can take some time, but normally all these cracks comes in within about month or two of the construction. This is drying shrinkage cracks, particularly not even in normal strength concrete, this may be quite a bit of this could be there. Other kind of cracks that comes out of shrinkage could be seen in this diagram. Typical concrete cracks, for example, this is K is fine crazing, this is crazing, this is called crazing, this is called crazing. You can see very fine cracks, surface cracks, crazing, C-R-A-Z-I-N-G, crazing, fine crazing. These are surface cracks. This also comes because of shrinkage, but DEF. So, this E, this D, where is D? D, E, F. So, this is E and D is here, D, E and F is here. These are shrinkage cracks. So, shrinkage cracks might appear like this. This will be largely surface. This might look at the surface, they might look like this, but if the section is thin, you might get them through and through also. So, these are the shrinkage cracks actually. A, B, C are plastic settlement cracks, but I think I will not discuss them, because I am not really discussing the cracks here. That is because of initial settlement. As I said, when bleeding occurs, the solid subsides and water has a tendency to come. If the reinforcement is actually restricting their subsidence, there will be a crack on top of it. So, these are plastic settlement crack A, B, C, at haunches where dimension change is occurring, you might see this kind of crack. Anyway, that is not of our interest much, but shrinkage cracks and crazing, these are of our important interest at the moment. There are other kind of cracks which I am not discussing, that would be part of some other discussion. So, this is the importance of shrinkage and shrinkage cracks. Now, next we can look into thermal expansion, which is almost a related matter to shrinkage and expansion, right, because this is also a kind of dimensional change. And you see, the coefficient of thermal expansion basically is important, because particularly, for example, if I am using a reinforcement, let us say steel, of course, we do use, and its coefficient of thermal expansion should be similar as the concrete. Fortunately, it is with respect to steel, they almost match, and therefore, there will be no if there is a differential thermal expansion, that will induce kind of tensile stress in one material with relative to the other, or compression in the other one. So, depending upon what is the coefficient of expansion. So, coefficient of thermal expansion of concrete is important. Aggregate does not expand much, right. It will of course depend upon aggregate type, right, and cement paste can expand. Aggregate expansion coefficient is different than that of the paste, and it has got a kind of restraining effect. So, stiffness or this modulus of elasticity are different. Therefore, one issue is coefficient of thermal expansion, other is the modulus of elasticity. So, net effect is it is actually alpha delta T is the alpha is the coefficient of expansion, which is length change per unit length. So, this will be kind of a strain, this will be the kind of strain, and stress induced would depend upon stress. This is the strain, and stress induced alpha is the coefficient of thermal expansion, and stress induced will depend upon the modulus of elasticity. Okay. Stress is multiplied by E, actually this multiplied by E will be the stress induced onto the other material. So, if it induces tensile strain in the concrete system, then it would actually cause cracking. So, it depends upon aggregate type, as I said, and aggregate content. Coefficient of thermal expansion of concrete varies within this, and steel is also somewhere there, 14, 13, 14, 11, depending upon type of steel, they are also within this range. So, coefficient of thermal expansion generally varies this. The factors those affect are actually moisture content, strongly affects moisture content, and also the the volume of aggregate, because you can see from this expression, this is the thermal expansion of concrete, this is the thermal expansion of paste and aggregate, this is the thermal coefficient of thermal expansion of aggregate, this is the volume of aggregate, G is the volumetric aggregate content, and Kp is the stiffness ratio of paste and concrete. So, modulus of elasticity of the paste to aggregate. So, this is also a function of this. So, these two factors, the modulus of elasticity, fraction, volume, and paste aggregate expansion coefficient, all this actually affects the coefficient of thermal expansion of concrete, coefficient of thermal expansion of concrete. So, this is an empirical sort of equation. So, this is what it is. Another factor which strongly affects is the moisture content or relative humidity. Moisture content or relative humidity. It depends upon like the moisture content affects most of the properties of concrete system, because the like thermal properties particularly, because if you look at thermal conductivity when you put in moisture, actually air is being replaced by air gets replaced by moisture itself, air gets replaced by moisture itself. Now, properties of air and water is quite different, and therefore, whenever there is a moisture or the moisture content of the concrete changes, most of the properties changes. So, the relative humidity and temperature, again temperature also affects the coefficient of thermal expansion. So, relative humidity, let us look at it. Now, it seems that when you have a relative humidity somewhere around 60% or so, somewhere around 60-70% or so, coefficient of thermal expansion is maximum. When it is saturated, it is somewhat less. It will depend upon stiffness. It will depend upon stiffness and stiffness of the, when it is saturated, of course, the expansion gets reduced. It will depend upon, besides that, when it is actually relative humidity is saturated, the stiffness also would change. Stiffness of the system will also change, because as we discussed earlier, the absorbed water actually changes the properties of the gel itself. So, depending upon the relative humidity, coefficient of expansion. So, it is actually observed that coefficient of expansion is maximum at about 70% relative humidity. So, most important properties which are there are the aggregate content, modulus of elasticity of aggregate, modulus of elasticity of the paste and paste thermal coefficient of expansion, and which is again governed by relative humidity or moisture content, and also dependent on temperature. It's also dependent on temperature. So, it is of course, there is some sort of some sort of observed experimental results. Relative humidity 100%, coefficient of expansion is something of this kind, and as my temperature at, of course, it depends upon -20 at low temperature. Now, this is more or less water will be mobile, in this, although the properties of gel water is different. It is not same as free water. It will not be like free water getting frozen. This may not get frozen at all, but properties are different. But as the temperature increases close to 0 degrees centigrade, this is lower at 100% relative humidity, but at higher temperature, which are important for us. This could be important if you are looking at the frost action, but as far as we are concerned, in Indian scenario, temperature will be higher than this, and this temperature does not have effect. So, low temperature has got some effect, and this effect depends upon again relative humidity. So, at 90% humidity, you can see the results are quite different, but as at high temperature, these are more or less similar. These are more or less, the values are more or less similar. So, this is what affects the this is what affects the this is what actually affects the coefficient of thermal expansion of concrete system, coefficient of expansion of coefficient of expansion of thermal expansion of concrete system. So, I think we have looked into so far, try to understand shrinkage a little bit from the fundamentals. So, in the process what we looked into, we tried to derive basically Kelvin's equation, and then we have tried to explain how surface tension properties can result in compression in the skeleton because of the nature of the water itself. Then we looked into as the drying occurs, it occurs from larger pores to the finer pores, and in the process it would exert pressure into the skeleton, and therefore, this compression will result in drying. This is what one issue we looked into. Then we looked into swelling mechanism because of the adsorbed water, how the surface tension of the gel itself will change, and how it is related to shrinkage when you have moisture, withdrawal or drying. And also, by the way, we just also explained that why compressive strength of concrete is lower when moisture is adsorbed, right. Of course, tensile strength increases, tensile strength of dry specimen is more, that is because there will be no shrinkage cracks. That is we talked earlier, and then we looked into various measurement method and their relevance of shrinkage in cracking. We tried to look into types of crack, and lastly we looked into thermal expansion of concrete system, the factors those affect the thermal expansion. So, with this actually we complete the module 7, where we have discussed largely about creep, shrinkage and related phenomena, and tried to also understood the creep behavior as much as possible and the shrinkage behavior of concrete and cement based material. So, I think that with that it finishes our discussion on module 7. Thank you.